Okay guys, in this video we've got a mock, a trial examination, grade 12 physical sciences, 2021. Okay, so we're gonna do it step by step. The first part of the video, let's look at the multiple choice questions. Even though they're multiple choice questions, please do not guess questions. You have to work it out. You have to work out the questions and get the answer. Okay guys, let's work it out. So let's start with 1.1. We are here. The rate of change of momentum is equal to what? So the keyword is the rate. Rate means something divided by time. The rate of what? Of the change of momentum. Change of momentum is delta P. Now, if you think of this quantity delta P over delta T, delta P means change. Delta means change. Delta P means change in momentum. So it's mVF minus mVi over delta T. You can factor out there m and remain with Vf minus Vi all over delta T. Now the quantity Vf minus Vi over delta T is acceleration. So this works out to Ma. And we know that Ma is the net force. So 1.1, the answer is A. 1.2, a spaceship descends towards the Earth at a rate of 9.8 meters per square second. The normal force that acts on the astronaut of 100 kgs inside the spaceship is what? Well, we know that normal force is a reactionary force that is applied by a surface. So if you have a person standing on a surface, the normal force will be the reaction to them pressing down on the surface. In the event that the surface is moving down at an acceleration of g, and the person themselves are also moving down at an acceleration of g, basically means there is no contact between, there is no reaction force between the surface and the person. There might be contact, but there is not enough reaction generated. So the normal force there must be 0, and the answer is C. Feels similar to what happens in an elevator. When the elevator begins to go down, initially feel like the support from your feet has been removed because the elevator accelerates downwards. The normal force lessens and you feel a bit funny down in your feet. But when the elevator accelerates upwards, it's almost like the downward press from the lift, from the floor of the lift, increases because the elevator accelerates in the opposite direction. Similar to that kind of scenario. Okay, 1.3, we are told a block of mass m descends a frictionless decline from rest. So from rest always means initial velocity is 0. Angle of inclination of the block, angle of inclination of the incline rather, is theta. If the acceleration due to gravity is g, what is the acceleration experienced by the block in terms of g as it descends? The only force that acts on the block is the parallel component of the weight. Okay, this is the force that will pull the block downwards. Now we know that if there is only one force that acts on an object, that force automatically becomes the net force. Okay, there's no other forces opposing this. There are no other forces opposing this. So we can see that MA is now equal to, well, FG parallel is equal to what? MG times the sine of theta. So one of the formulas, guys, you have to remember, weight parallel is equal to mg times sine theta. You can divide both sides by m. You remain with A is equal to g times the sine of theta. So our correct answer is g sine theta. And that's the answer there, B. 1.4 says a ball is dropped from a certain height, again dropped, means initial velocity must be 0, you're dropping it. Ignore the effects of friction and assume that the collision of the ball with the ground is elastic. So this ball is bouncing to the same height. If an object collides, especially a ball, if it collides with a wall or a ground, it means it's going to have the same velocity as it struck the ground or the wall with. In the case of the ground, it means the ball must reach the same height. Okay? The point of release is the reference point, and take downward motion as positive. Okay, so as the ball is falling downwards, it's going in the positive direction. And when the ball bounces upwards, it's going in the negative direction. A little bit confusing, but that's what the question requires us to do, and let's do that. Which of the following graphs shows the correct position time of graph for the motion? Now, for projectile motion, position time graph, in the absence of friction, we expect the curves for the graph. So this automatically means A and B are out, because A seems to be a velocity time graph and B seems to be an acceleration time graph. There are no curves there. So the only possible answers could be C and D. Position time graphs for projectile motion, we're expecting some kind of curved motion. We're always expecting some kind of curved motion. Okay. Because the rate of change of velocity of displacement, the velocity is not constant. The velocity keeps changing. All right. Now, as the ball falls downwards, the velocity increases, the speed increases. All right, the speed increases. Now, on a position time graph, we know that the gradient is the same as the change in displacement over time, which is the same as the velocity. So we're looking for a graph that shows that as the object falls, initially velocity is 0, velocity is a max when the ball is just about to hit the ground. Okay, if we look at C, C is showing us that this is what's happening to the gradient of the graph. Initially the gradient starts off high, but then at some point it levels off. So it's telling us that the ball is starting from a high velocity and slowing down. This is not consistent with the idea of dropping a ball. If you drop a ball from rest, then the ball is going to increase velocity as it goes down. So C is out. If you look at D, D is showing you that the gradient of the graph starts from a slow value and begins to increase as you go up, which is consistent with the idea of dropping a ball. So the correct answer for this question must be D. 1.5 says two identical metal spheres, each of mass m and separated by distance r, exert a gravitational force of magnitude F on each other. The distance between the spheres is now halved. The magnitude of the force the spheres now exert on each other is what? Now, this is the case of Coulomb's law, or rather Newton's law of universal gravitation. Don't mix them up like I do. They are very similar, so I rushed for Coulomb. Okay, but it's actually Newton's law of universal gravitation. From this, we discover that the force is inversely proportional to the squared distance, and this gives us this idea of the inverse square law. How the inverse square law is simple. Identify the factor, invert it, and then square. Now they say the distance is now been halved. So the factor here is a half. What we're going to do to the half, we're going to invert it. First step, invert. Inverse of half is 2 over 1. Second step, square the 2 over 1. What is this? 2 over 1 squared is the same as the 4. So which means the new force is going to be 4 times the old force. And our correct answer there must be D. 1.6 says, in the diagram below, a current carrying conductor carrying current into the page is placed between two magnets. Okay? So the moment we deal with current carrying conductor, remember our two rules. It could be the right-hand rule or the left-hand rule. Which one should I use here? I should use the left-hand rule for the motor effect. And the way I always remember it, I always say FBC, football club. Right? F, force, the B represents the magnetic field and C is the current. So in that order, your thumb, and then there's the forefinger, and then there's the middle finger, like that. So the force, the B field, C current. Now, we can always try by taking this finger first. This is where the field is. So, if this finger points into the direction of the field like that, and then your middle finger goes into the page, because that's the current, you'll find that your thumb will point downwards. Okay, so the direction at which this current conductor will move is position 3, downwards. 1.7 says a line emission spectrum. So the keyword is emission spectrum. So emission spectrums are normally for when objects are glowing and they're already hot. So they glow or because they are emitting colors. For example, if you hit a metal, it can turn to red hot. Then it can sometimes become yellow hot. Then sometimes it becomes white hot. So what's happening is that red hot, it means the metal is emitting red colors in the red frequency. Yellow hot, it's emitting colors in the yellow frequency. White hot, it's emitting all colors, so it appears white. So emission line spectrum is obtained when light is passed through a cold gas. No, the cold material will absorb energy. From a hot gas, yes. When the gas is hot, it's going to give off a color. So the correct answer there is B.
1.8. Which one of the following graphs best represents the ratio between electrical power and the current in a given ohmic conductor? Now, there are three power equations that we need to be aware of. One of the power equations says P is equal to V times I. The one says P is equal to I squared R. And the one says P is equal to V squared over R. Now we want the one that has got power and current. So this one and probably that one. But this one has got P and I squared. Okay, so let's deal with this graph. Now, we are told that we're looking at an ohmic conductor. So in an ohmic conductor, we already know that the voltage and the current have a direct relationship. In other words, let's say the current is 1, then we double it to 2. Let's say the voltage value there is 2. Doubling the current, the voltage also doubles and becomes 4. That's a direct relationship. So, if we use this information to plot a graph of V versus I, rather of P versus I, the power versus current, and we use the same current values 1 and 2. Now, we'll notice something interesting. Now, when the current is 1, what will the power be? We say power equals voltage times current. It will be 1 times 2. So when the current is 1, the power is 2. All right? Get this point here. But what happens now when the current is 2? Using the same approach, the current is now 2, the voltage is now 4. So we're going to have 2 times 4 to give you 8. That's a sharp increase from the previous value. So you can clearly see that this is not following a linear relationship. This is actually following some kind of exponential increase. Okay, so which graph best suits this? It's D. The correct answer there would be D. So sometimes with this kind of questions, you can put in imaginary values and develop a relationship and see how it goes. Okay, in this case, we need to know how the voltage also changes. So as you increase the current, the voltage increases by the same quantity, by the same factor rather. Okay, so which means the power increases rapidly. It doesn't increase linearly. So the correct answer there would be D.
In 1.9, we're told the two resistors in circuit 1 below are identical. They're connected in series to a cell of EMF V and negligible internal resistance. The power dissipated by each resistor is P. So there's circuit 1, there's circuit 2. The two resistors are now connected in parallel, shown in circuit 2 below. So in circuit 2, they're in parallel. The power dissipated by each resistor is going to be what? Well, we say the power dissipated by each resistor is P. By what factor does that power change? Well, our power equations are P equals VI, P equals I squared R, P equals V squared over R. Now, you can use any one of these equations. We should get the same answer. Okay. If the idea of relationship sometimes is difficult to work with, I would say use values. Why not use values? If you use values, it can become quite easy. For example, I'll say the voltage is 4 volts. The resistance is going to be 2 ohms. Okay. Now, which means also the resistance there is going to be 2 ohms. Now, which equation for power can I use? Well, the easiest to use for me would be the last one, P equals V squared over R, because I can easily work out the voltage of each resistor. Here, we've got 4 volts, so the volts will be divided. So here I'll have 2 volts, here I'll have 2 volts. In parallel, the voltage will be the same, so I'll have 4 volts there, and I'll have 4 volts there. So, the power of a resistor in circuit 1 will be V squared over R, V squared, which is 2 squared over 2. 2 squared is 4, 4 divided by 2 gives me 2 watts. In circuit 2, the power will be V squared, which is 4 squared divided by 2. 4 squared is 16. 16 divided by 2 gives me 8 watts. So you can see that now, if I take the ratio of P2 over P1, I'm getting 8 over 2, which is 4. So P2 is 4 times the original power. The original power is P, so the answer must be B, 4P. That's one way of doing it. Put values, but make sure the values are the same. For example, this case is 2 ohms, 2 ohms, 2 ohms, 2 ohms. The total voltage is 4. That's one way of doing it. So I can see that the answer is B. Well, What if I don't use values? Can I explain it now without using values, without necessarily performing a lengthy calculation like this? Yes, I can, by understanding these equations and how they work. So let's see how that would work as well. Let's use the blue pen. So let's start with the first equation. P equals VI. So if we imagine that the current that flows in this circuit is I, then what will be the current that's flowing in this circuit? Well, we already know that the total resistance here is going to be 2R, because it's R plus R. Here the total resistance will be 1 over R plus 1 over R, 2 over R. The total resistance should be half R, because if you take the 2 over R, you need to invert it. So the total resistance is a half R. So from 2R to half R, you see that the resistance decreases by a factor of 4, because 2 divided by half will be the same as 2 times 2 over 1. The R's cancel out, 4. So the resistance decreases 4 times. So the current here must increase 4 times. So the current is 4I. The current is going to split, which means in each resistor I'll have a current of 2I. Okay, so now I've got current, I've got resistance. So I'll say the initial power for circuit 1P is going to be V times I. Now the voltage of each resistor, what is the voltage of resistor going to be? The voltage here is going to be divided. So here it's going to be a half V and a half V. Here the voltage is not going to be divided, it's going to be V. So in the first circuit, the power is going to be I times half V, or VI is half V times I rather. This is the same as VI over 2. In the circuit 2, the power is going to be VI, but the I is 2I. So it's going to be V times 2 of I, which gives you 2VI. Again, if you work out the ratio of the new power of the old power, you get a factor of 4, which means the power increases by 4. In other words, if you say 2VI over a half VI, you get a factor of 4. So the power is gone up by a factor of 4. So this again is the correct answer. And again, you can use values. Okay, so for practice all this type of question with all these formulas. Use values. You can use the technique of using values, or you can just use the I and the R and determine the voltage, determine the quantities that you want to use using the symbols provided, and feed into the equation. See how the new power changes. 1.10. When light of a certain wavelength is incident on a metal surface, no electrons are ejected. Which one of the following changes may result in electrons being ejected from the metal surface? Well, we know that the intensity of the radiation does not affect the energy of the radiation. Intensity affects the number of photons that are arriving. If you increase the intensity, you increase the number of photons, you don't increase their energy. If you use light with a shorter wavelength, we know that frequency is inversely proportional to wavelength. The shorter the wavelength, the higher the frequency. And the energy of radiation is directly proportional to the frequency. So B would work. Using light with much shorter wavelength would increase the energy of the radiation, because the energy is directly proportional to the frequency, whilst the frequency is inversely proportional to the wavelength. Or we can also say the energy of the radiation is inversely proportional to the wavelength. Decreasing the wavelength increases the energy of the radiation. So for multiple choice questions, that's it for now. In the next video, the next series of this video will focus on the longer type questions where we do calculations.